Então, a doutora Olinda Monteiro licenciou-se em Engenharia Química na Faculdade de Engenharia da Universidade do Porto, e foi assistente no Departamento de Química da Universidade da Madeira entre 94 e 97. Depois iniciou o seu doutoramento em Química aqui na Universidade de Aveiro, sob a orientação do professor Tito Trindade, tendo terminado em 2003. Desde essa altura, que realiza investigação no Departamento de Química e Bioquímica da Faculdade de Ciências da Universidade de Lisboa, inicialmente como pós-doc e a partir de 2007 como investigadora auxiliar. É membro do Centro de Química Estrutural e a sua investigação tem-se focado no design, síntese e aplicação de materiais semicondutores nanocristalinos. Tem especial interesse na síntese e funcionalização de novos materiais nanotubulares para o desenvolvimento de novas plataformas nanoestruturadas para aplicações fotocatalíticas, nomeadamente para a remoção de poluentes emergentes. Ora, eu quero desde já agradecer a Olinda ter aceito este convite, porque sei que ela tem estado bastante ocupada, como já tivemos a oportunidade de ouvir dizer, com as aulas todas concentradas nestas primeiras semanas, e dou-lhe a palavra.
So, hello, good morning. Marcia, thank you for the invitation and for this nice presentation. So, I'm here to speak a little bit about Titanate elongated nanostructures. But before to start with this topic, I would like to ask you to look for this slide and please try to answer this question. Well, probably I cannot see you, so I will answer for you. This is my answer and of course our answer to this question. These are pharmaceutical and personal care products and are now very problematic because they belong to a new class of pollutants that are the emergent pollutants. Why? Because, well, this is not only our answer, this is our family answer, our friends, our neighbors. So all of us need these products, and if we think a little bit, after use, these products goes to the environment. So they are not degraded in natural conditions, so they will remain in the environment. They can combine with each other, forming new products with very dangerous properties. They accumulate there, and we are now starting to see these products in very different places, usually in water systems. So if we are part of the problem, we must be part of the solution. What is the solution? And this is the question. Of course, we can decide that no more products tomorrow morning, but I think this is not realistic. So, of course, we can think green when we go to the supermarket to try to buy these products, but we can also need approaches to try to decompose these products. As you can imagine, by this time, I'm talking about photocatalytic degradation process that can be used to degrade these products. So how this works? We have the sun that will be our energy source. It's free, so excellent. And we are looking for a catalyst that under irradiation is able to produce this oxidant species that will be responsible for the degradation, oxidation of these organic pollutants. And if we start to talk about photocatalytic process, we must talk two lines about TiO2. TiO2 is the most used photocatalyst by these days. Why? Because, well, TiO2 is not the ideal catalyst because, as you can see, it has some drawbacks, but at this moment is probably the most interesting material to be used in this context. Well, why TiO2 is not the ideal one? Because first, it is only activated, TiO2 is a semiconductor material, but it's only activated under UV radiation. So if we have TiO2 under sun conditions, a very small fraction of the radiation from the sun is used by this semiconductor. But when I irradiate this material with this energy, I will be able to have an electron in the valence band that will transit for the conduction band. And it will have all the conditions to be used in some oxidation or reduction reaction. But this is one problem, the radiations that we need. The other problem is the recombination of these electrons here in the conduction band, because they are so energetic, but they want to recombine again for the valence band. And if we want to have the electron here to participate in some reactions, I must avoid this recombination. But this is TiO2. We propose the use of titanate elongated nanostructures. Why? Well, they are very similar from the structural point of view. They are very similar to TiO2. We have the TiO6 octahedra here, but they have a layer layout, and between these layers of TiO6 octahedra, we have some sodium plus ion that can be very useful if we want to play with these materials. And of course, if we have a layer material, we will have a higher surface area. But as I told you, they are similar, so we would like to improve even more the photocatalytic properties of these materials. And for that, we have two things that we can do. We can try to shift this absorption, this energy, from the UV to the visible range, and I will start to have activity under visible light. Or I can try, I can try to reduce the recombination of these charge carriers. How? Well, I can try to introduce some extra energetic levels here in this forbidden zone in order to make more difficult the process of the recombination of the electrons. We have been working for this for a couple of years. We have working with titanates, and we have different approaches in order to modify the optical and photocatalytic properties of these materials. And today I will have some examples about these works. But before we think about modify these materials, we need to prepare them. How? Well, we have a methodology developed by us. We use titanium trichloride, that is a non-toxic material. We prepare a precursor, then is submitted to hydrothermal conditions. And if we use sodium hydroxide, we will be able to prepare titanate nanowires. Or if we decide to use water as solvent, we will have anodized nanoparticles that then can be used to prepare titanate nanotubes. And just to have an idea, playing with the time and temperature of this process, we are able to control the morphology of these materials. We can have nanowires, nanofibers, or nanotubes. So this is the structure of our titanates. What is the easiest thing that we can do with them? Well, we have this sodium here, so why not try to replace this Na plus with the proton H plus? And we are interested in remove some of the sodium and replace them by H+. Of course, in the limit, we will be able to remove all the sodium in the interlayers and we will have H+ here. And as you can see, it seems that this distance between the layers decreases. In fact, to have these materials, we just need to put our titanates, nanotubes, nanowires, or nanorods in an acid solution, control these conditions, and then we can see here, we can control the dimension of this interlayer. And with this, we know the amount of sodium or proton that we have in this material. And of course, at the same time, we are preparing some materials with different photocatalytic activity for the degradation of pollutants. But one thing is to replace the sodium plus, but we can also think about doping this material. How? Well, we want to replace some of the titanium that is here in the octahedra, and we would like to replace some of this titanium by a metal. And then, if we have this new material with titanium and metal here, of course, the sodium is exactly in the same place, but we can think also in replace this this sodium by the proton, as I told you before, and we will have a material with proton and with dopant. And of course, in the limit, I will be able to have a completely protonated material doped with a metal. Just a brief example about this. Imagine if we prepare titanate nanotubes under these conditions. I must say that the time and temperature plays a very important role in these processes. As you can see here, we have more or less the same dimensions of our particles. If we look for the XRD, we have no changes in the structure. But of course, if we look for the optical behavior, the optical spectrum, we can see that when we have the incorporation of cobalt as dopant, we start to have absorption in the visible. Just to show you how this can be important when we talk about photocatalytic degradation, we can look for this picture, and as you can see, when we replace the sodium by the proton, we have an increase in the performance of the photocatalyst. Also, if we use a doping system, in this case with the cobalt. So now we know how to replace the sodium by the proton and how to prepare doped materials. But why not try to replace the sodium by a metal, ionic metal, of course. So in this case, we are thinking about to replace some of this sodium by the metal, ionic metal. Of course, we can think about this using a doped material, or if we want, using the pristine titanates, we can replace this sodium by the metal, some metals. And of course, if we want to go further, we can think about to replace all the sodium in the structure. And this is very interesting because with this, we will be able, for instance, we will have a material, this one, that has TiO6. So we have only the metal in the interlayers. If we look here, we have metal in the interlayers, and it can be the same metal, but in a different position, replace some Ti4+, or I can have this metal, in this case, in a position replacing the titanium. So this can help us to study the influence of the position of these metals in the structure of these materials. Well, we know how we can prepare the pristine samples. If we want to prepare the doped samples, we just need to add the metal that we want when we are preparing the precursor. Of course, not all the metals work in this process, of course, because some dimensions and some other problems, but we have a lot of experience in preparing this kind of material. And with this, we will be able to prepare doped materials. If we are interested in put the metal only in the interlayers, I just need to put our material in contact with a solution where we have the metal, and in the end, we will be have to replace part or the totality of the sodium in the structure. One example that is that tell us that sometimes this doesn't work in the lab. So we have prepared the precursor, hydrothermal treatment, and we have prepared titanate nanotubes. Then we decide to use this material to remove H+ from water. And of course, we have an ion exchange process, and we will have titanate nanotubes with H+. Then we decide to use this material under UV radiation, and we start to see the formation of some particles, silver particles. And of course, if we increase the time of radiation, we will have the formation of more nanoparticles. And when we use this material for the photocatalytic degradation of phenol, we can see that, in fact, this material is a better catalyst than the first one. So why not try to degrade phenol at the same time that we are preparing the photocatalyst? So we decide to study this point. We start with the titanates with H+, and use this sample to degrade phenol. First time, second time, third and fourth cycle. And as you can see, it seems that the amount of silver is increasing in our sample. And as you can see here, in fact, the XRD tells us that we have more crystalline silver nanoparticles after 4 cycles. And how about the phenol? We have performed this at the same time that we are trying to oxidate phenol. So as you can see here, the performance of these 4 solids is fantastic. We have 100% of degradation of phenol. So this tells us that using this material or this one is the same in terms of phenol photodegradation. Why? If we have different particles in the catalyst? Well, after some studies, we concluded that, in fact, when we are using the activation of this material, the electrons that are here in the conduction band have energy enough to participate in the reduction of the silver plus. So that's why we are creating more nanoparticles of metallic silver. But of course, the performance, the catalytic performance is the same, because the silver, it's also catalytic for this process. So we have the formation of these species that will be in charge for degradation of phenol. So it seems that everything is perfect. I just need to tell you that, well, but in our system, we didn't have H+ in solution. So where this H+ comes from? From the interlayers. We have the H+ in the interlayers that migrates to the surface in order to be able to produce more silver nanoparticles. So this was a very interesting work. So let's go back again to our titanates, and why not try to put here something more than H+ or some metal ions? So we decide to investigate the possibility of have more bigger species in the interlayers. We decide to this work trying to use these materials to absorb some organic species. We have tested some dyes, and the results are this one. So if we start to use, in this case, we were using titanate nanofibers, and if we start with the protonated nanofibers, we have no success in the immobilization of this species. But when we use the titanates with sodium in the interlayers, we can see here that in fact we have an adsorption that is very high for these materials. Of course, in the case of rhodamine G, we have no adsorption, and this is because of the steric effects that we have in this molecule. So we decided to investigate how these molecules are connected, linked to the surface. Well, we decided to think about two limit situations. We have all of our molecules in a flat position or in a perpendicular position in relation to the surface. And after some measurements and some calculations, we can see here that, for instance, for thionine, our material is a nanofiber, so the surface is not so big. We have this surface, and in fact, to have all these molecules only in the surface, we need this area that we don't have. So this tells us that we don't have only adsorption, or if we have it, we don't have a monolayer formation. We have a multi-layer. Okay, but we decide to think about the possibility of have these species because they are a kind of planar molecules. Why not try to think about intercalation of these species in the interlayers? Well, if we look for the interlayer distance, well, it's not far away from the size of the molecules. So we are thinking in this possibility. We have, of course, some adsorption in the surface, but we are thinking in incorporate these species here in the interlayers. And in fact, when we look for the XRD results, and I must tell you that this signal at more or less 10 to theta is related with the interlayer distance of these materials. So when I start to treat these particles with thionine, I start to see a shift. So this telling us that we are playing with this interlayer distance, and this tells us that in fact we have intercalation of these species in the interlayers, in the space between the TiO6 layers. Of course, when we analyze the samples with the protonated samples, we have no changes in this peak. Of course, in this case, we didn't use these materials for photocatalysis, but we try to combine these results in a different way. We decide to use a doped material with cobalt. We decide to combine these particles with this dye, and we had this adsorption spectrum for the particles. And these particles are almost dark, black. And when we put these particles under UV radiation, as you can see here, they are very stable. So probably they are not interesting for photocatalytic degradation, but they can be used for other photo based applications. Other example is, for instance, why not try to modify this titanate nanostructure with a second phase, a second semiconductor phase. Here we decide to study the sulfides, metal sulfides nanoparticles. We have used single source precursors. And as you can see, we are able to prepare different materials with different morphologies. In this case, we have nanocrystallites of zinc sulfide. In this case, they are also some very, very small nanocrystallites, but these are islands of small crystallites. And here we have a kind of sheets surrounding the type, because this bismuth sulfide is a laminar semiconductor. Of course, this is interesting, but as I told you before, we are more interested in look for the photo behavior of these materials. These are the spectra, the reflectance. No, sorry, these are not reflectance. These are absorption spectra, and here we start to have absorption in all the visible range. In the case of cadmium sulfide, we start to see here contribution of the CDS crystallites for the absorption of material, and here we can see the contribution of this naked surface of the titanates. Of course, in the case of zinc sulfide, the difference are not so evident, but this material is very interesting when we are looking for a material that contributes to reduce the recombination rate. And that's why we use zinc sulfide. So we are interested in combination that allow us to introduce extra levels, energetic levels, of course, in order to make more efficient the use of materials as photocatalysts. Of course, this is only some schemes, and if we want, well, depend on us. And here is an example where we have combined zinc sulfide nanoparticles with silver sulfide nanoparticles. This is a kind of core shell system, and in fact, the photocatalytic performance of this nanocomposite, it's very promising due to the recombination of these three components. But I would like to show you this material, that is the combination of bismuth sulfide and zinc sulfide nanoparticles in the surface of titanate nanofibers. We have prepared this. This is the bismuth sulfide and the crystallites of zinc sulfide. As you can see here, it's easier to see the sheets of bismuth sulfide and some small dots that are the zinc sulfide. Of course, we know that if we are using bismuth sulfide, we will have an increase in the absorption of this material, but I would like to show you a different way to see these materials. Imagine that we test these titanate nanofibers to remove, in this case was methylene blue dye. So this is normal degradation. You turn on the light and you start to decrease the amount of dye that you have in solution. However, when we start to use the nanocomposite with bismuth sulfide and zinc sulfide, this is our stock solution, and of course we have a dark period to allow the absorption, and after that, this is time 0 when I turn on the lamp. So if we look closer, where is the 0? Is here, okay? I turn on the lamp, and this is 20, 30, 45, and then I start to decrease. So it seems that in the beginning, the concentration of the dye increases in solution. We have the lamp turn on, we have radiation, and only after 45 minutes we start to decrease the concentration of dye in solution. Why? Well, we need to think that bismuth sulfide, it's a very good adsorbent, especially for cationic species. So when we put this material in contact with the solution with the dye, we remove almost all the dye from solution, and then we can take the modified material to the lab, to the lamp system. We put it in water, and we start to see that and we turn on the lamp. So we have degradation of the dye. At the same time, we have absorption for solution. And of course, here we start to have more degradation than absorption, of course. And here in the limit, we have completely recovered our material that can be used again to remove dye from a solution. And this is very interesting because we are combining in two different processes. Adsorption, we are removing the dye from a solution by adsorption, and then we recover the material by photocatalytic degradation of this dye. Now, until here, well, I think everything is easier, I think, but now I would like to show you one example of how these things work in the lab. Of course, sometimes it's not so easy for us to conclude something about a material. So I have one example to show you all the steps that usually you use in this kind of system studies, okay? The example that I have is related with the preparation of materials with 1% of ruthenium, and we would like to compare Titanate nanotubes and nanowires. Is it different? Have nanotubes or nanowires? Well, let's see. We start to prepare a precursor with 1% of ruthenium, and then we decide directly to prepare ruthenium titanate nanowires here, and with using exactly the same precursor, we have first prepared TiO2 with the ruthenium, and then prepare the titanate nanotubes that are here. Well, as you can see here, the amount of ruthenium that we have is different. Well, why? Because we are using the same precursor. Well, we are lost some ruthenium in this time because we have a two-step process, and that's why we lose some of this ruthenium. Well, if we are interested in use these materials for photocatalysis, it's very important to know the surface area of these materials. This is the BET surface area, and as you can see, for nanowires, we have almost no differences. It's not the same when we are talking about nanotubes. We have difference from the ones preparing with the ruthenium or without ruthenium. After that, we need to know where is the ruthenium. As I told you, we can have ruthenium in the interlayers or doping, replacing the Ti4+. And if we look for the XRD results, we can see that, of course, we can calculate the size of the crystallites, and we can see in both cases we have a decrease in the particle size of these crystallites due to the incorporation of ruthenium. But if I focus in this peak at 10 to theta, I can see that, in fact, when we have the nanowires, we have a shift in this value. And this tells us that we have changes in the interlayers. And this means that we have some ruthenium here in the interlayers. And that's why our distance here is different, okay? For the case of titanate nanotubes, we have no changes in these parameters, so we are not expecting to have ruthenium in the interlayers. Then we decide to analyze the Raman results. And as you can see here, when we talk about titanate nanotubes, we have no changes in vibrations. But when we look for nanowires, we can see that the values are different. And if we compare these values with the sample that was prepared with the ruthenium only in the interlayers, we can see that this telling us that for this material, we have some of the ruthenium in the interlayers. Of course, we need to confirm this by XPS, for instance, and as you can see here, these are the core spectra for the TI 2P energies, and we have for we have a small shift here. Sorry, it's not very visible. We have a shift in these peaks that tell us that we have a difference in the density of charge surrounding the titanium atoms. And this is associated with the presence of some ruthenium replacing titanium. And we had these results for nanotubes and also for nanowires. So we have ruthenium replacing some titanium. Of course, we have confirmed the presence of ruthenium in our samples. But we are also very interested in the optical behavior of these samples. So these are the optical spectra of the nanowires and the nanotubes. And when we combine this information with the one coming from the valence band XPS spectra, we are able to do some calculations and then to know exactly where is the valence band and conduction band of these materials. And as you can see here, we have some shifts when we have the ruthenium in the nanowires and also in the nanotubes. We have an increase for negative values, of course, here in the conduction band, and the same for the valence band position. Also important is, now that we know the exact position of these bands, we know that we can have some transitions here due to the presence of the ruthenium. We know the potential of the redox reactions of a ruthenium species that can be from donor or acceptor type, and are very important to play here in these forbidden zones. After that, we have the materials characterization finished, so we need to start to study the photocatalytic performance of these materials. Usually, we start with the terephthalic acid. Why? Because it's a model molecule that degrades via hydroxyl radical, producing this species. And we are able, for using fluorescence spectroscopy, to detect this molecule, this species. And as you can see here, when we turn on the lamp, we can see that, in fact, our samples with ruthenium are better photocatalysts for this process than the ones without ruthenium. But of course, these two are also catalytic, but the ones with ruthenium are the best ones. And the best one is the titanate nanotubes with ruthenium. Okay? And now that we know that we have chances to have good photocatalyst materials, it's time to try to use these materials for the degradation of some other pollutants. In this case, we tried caffeine and sulfametazine molecules. As you can see here, once again, we have better performance, photocatalytic performance for the sample ruthenium titanate nanotubes. And this one is also very interesting. And if we think a little bit, I don't know if you remember, but this sample is not the one that has higher surface area, but is the best one. Well, why? Well, we don't know, probably we know, but we need to think a little bit more about this, why the nanotubes are better than nanowires. But what we know is when we compare the intermediate products that are forming during the irradiation, that is also a very important parameter if you want to study the toxicity of our proposal, okay? And if we compare these two time profiles, we can see that, in fact, using ruthenium nanotubes or ruthenium titanate nanowires is not the same in terms of formation of byproducts. So this telling us that probably we have different mechanism of degradation of the caffeine in this case. But as you remember, I told you that we are interested in try to shift the absorption edge of these materials to the visible, and we are also interested in try to see if we reduce the recombination of the charged carriers. For that, we decide to repeat these experiments under visible light for sulfametazine and caffeine. And in fact, when we have the ruthenium doped samples, we have better performance than the ones that we have for the pristine materials. This is under visible light. When we look for the photoluminescence spectra of these powders, and these are emission spectra, we can see that, in fact, when we have the ruthenium in the structure, we have a very low emission spectra. And this is because we have a more efficient separation of the electron hole in the system. Why? Because we have ruthenium there that acts like a electron trapping sites. And only after all these studies, we are able to propose a mechanism for the activation of these materials. In this case, we have the role of ruthenium species that are here in this forbidden zone, and then help us to have a better photocatalyst system. And of course, when we do these studies, in this case was for sulfametazine and caffeine degradation, but sometimes we need to think about, and if we have a more complex pollutant, well, we have tried to use these materials for the degradation of trazodone, that is here, this molecule. And in fact, when we study different, in this case were nanowires, for the degradation of this antidepressant, we have excellent results. So this tells us that, in fact, these materials have all the conditions to be used for the removal of more complex matrices. So, and with this, I'm finishing. I hope now you think like me, titanate nanostructure are excellent materials to be used when we want to modify or we want to control some properties of these materials. Of course, today my focus was the degradation of pollutants. We are now using this material not only to destroy something, to degrade pollutant, but also to protect or to create something new. But this will be for the next talk. So I would like to thank you for your attention.
Thank you, Olinda. for the very nice and interesting talk. Now we are open for questions. Someone? No?
You can start, Marcia.
Yeah. So in the first example that you gave us, what is the role of the cobalt in the photocatalytic process?
Sorry, I didn't have time to show everything, of course, but in this case, the cobalt is also participating with some intermediate levels of energy in forbidden zone.
Like the silver particle?
Sorry?
Like the silver, when you have...
like ruthenium.
Okay. Like in this last example. Okay.
Yes, because this depends on the energy that you have for the cobalt.
Okay.
That belongs forbidden.
In these last slides, you have explained that sometimes it's useful to check what are the final products of the composition.
Yes.
And you didn't show for phenol. I think you use lots of time phenol.
Yes. Why phenol? We like very much phenol because phenol appears as a byproduct of other more complex pollutants degradation systems. So when you start to a very complicated pollutant, in the end, you will have somewhere phenol. And phenol is very complicated sometimes to be degraded. Well, I don't have here in this presentation the byproduct of phenol. It's very interesting because they absorb in the same range and they are very similar to phenol. We have this kind of studies, but sorry, I didn't have time.
Okay. You know, I like morphology of particles, okay? So I will ask you, how do you compare the morphology of the second phase of the semiconductor in your titanium tubes or fibers with the ones that we once produced in silica or in titanium dioxide nanoparticles?
Sorry, I didn't understand your question.
So you have one work where you prepare a second phase of a semiconductor.
Yes.
So morphology of those particles are similar to the ones when you use the same method in silica or in titanium dioxide?
Depends.
Phase?
Depends. Sometimes you have exactly the same morphology is more or less the same. But for instance, the particle size of the crystallites are different and are dependent if you have the titanates there or not. Okay. So usually, for instance, for CDS, you have smaller crystallites if you prepare them in the surface of the titanates. Okay, so you have some influence of the titanates in the morphology, not exactly the morphology, but the particle size of the particles.
And it's different when you prepare the titanates with doped metal? No, because the structure is the same.
This is a very interesting question. You know, I showed some results where we had cobalt doped particles that were exactly the same size of the pristine sample. But if you change the conditions, it's not true anymore. You can prepare, for instance, for us, it has been completely impossible to prepare doped nanofibers. Don't ask me why, but we're not able, because we can use exactly the same conditions that we are using to prepare titanate nanofibers. But if we put a dopant there, we always have fibers or tubes, not fibers, sorry, wires or tubes, not fibers. we're not able to prepare big particles, dopper. Don't ask me why. Well,
Okay.
we try, and then we have some hypotheses, but we are working on this.
One last question. It's about very interesting studies that you made with bismuth sulfate and the zinc sulfate.
Yes.
Did you try to absorb another molecule in the bismuth sulfate, and because you try with the methylene blue, right? Mm-hmm. Did that effect of the absorbment appear with another molecule? Oh.
Yes, bismuth is very good when you try to absorb or immobilize. Sometimes I prefer the word immobilize because sometimes you can have it in the interlayers. You can have it for cationic species, okay? Sometimes we use bismuth sulfide only because it is a very good adsorbent for cationic species. Okay.
Okay. So once again, I thank you. And if there isn't any other questions, obrigada, Olinda.
Obrigada.
Trabalheira que isto te deu.
Tchau, obrigada a todos.